Hello. Now we start our course of calculus. So to start with, we shall expose real numbers. And why real numbers? Because since we said that we deal with differentiation and integration of what? Of functions. And functions work on real numbers. So we have to first explain what the meaning of real numbers, how to deal with them. Now, in this first lecture, we shall be studying the following. First, we shall be displaying the meaning of sets and real numbers. And then we shall be speaking about algebraic and order properties, the intervals, again, the meaning of inequalities, the meaning of neighborhood, which is of paramount importance of the subject of limits, and then the Cartesian product, and that will be the end of this lesson. Now, to start with sets and real numbers, the meaning, of course, what the meaning of a set. So the meaning of a set is clear here. The definition is this. It's a list of objects that you put them or you classify them together. Usually, sometimes they don't have things which are or relations that are relevant to them, but most of the time they must have a certain adhere or comply to certain properties. Like, for example, you say the set of even numbers or the set of prime numbers. So they stick somehow to a certain rule among these objects. When you have, for example, a set A, an aggregation of objects, and you have an element in the set X, when you say X an element of A, it's meaning it's an element in the set. Like, for example, you have the set of natural numbers. This is the set, the most famous set, which we count on our fingers, 1, 2, 3, etc. Some mathematicians, they add the number 0. I don't. And if you have, for example, a number like 2.5, of course, it's not an element in the set. So what you do, you set the symbol of element, and then you discard it, meaning that you cancel it, meaning that 2.5 is not a natural number. Usually, mathematicians use what's called Venn diagrams. And Venn diagram, they have a universal set, which contains all the possibilities that you have. And then, for example, you have the set of students, and you have the set of students who have succeeded, for example. So you say, if you pick a student at random, so either the student have succeeded or the student has failed. So X is an element of the set of successful students. So X is an element in A, or X is not an element of A, and meaning that the student have failed. This is when you have one set. When you have two sets, like, for example, you have the set of students who have succeeded and the set of students who own cars, then and you choose at random a student. So either the student has succeeded and own cars, or he had succeeded, or he doesn't own a car, or etc., or he owned a car and failed, etc. So you have four only possibilities. Either X element in A and B, which is the region in between, the region 1, or X element in A and not in B, or X is not element in A but is an element of B, and finally, when the student has failed and doesn't own cars, for example, you have it's neither in A or now nor in B. So instead of writing X element in A or B, or lying in A and in B at the same time, in other words, having the property of both sets, for example, mathematicians resorted to notations called union and intersection, and these notations will be introduced in order to gather these properties. For example, here we have something called A union B, meaning that the set X is either located in A or in B or in both. We can always have something called the intersection of two sets, and the intersection means that the X lies in both A and in B. In other words, lies in the region between them, the shaded one that we here clear on the slides. We can also have what is called A but not in B, like the one that we saw in the slides before, meaning that, for example, the set of students that have succeeded but do not own cars. So X is element in A but not in B. So we use this slash here, meaning that the set A, but those elements in A that are not at the same time elements in B. We can also use the complement of A, meaning that the set which comprises those elements that do not possess the quality or the property of A. like the shaded one here. So now we can have some algebraic laws of sets. Like for example, the first one is called independent laws, that A union A, of course, is equal to A, or A intersection A is equal to A. You have also commutation, like A union B is equal to B union A, etc. We should not be dwelling much on that because the students might be aware of this. We can also have some distributive laws, like A union B intersection C is equal to A union B intersection of A union C. These, as a matter of fact, resemble very much those of numbers. And you have identity laws. This is called the void set. So A union void is equal to A. And U is the universal set. In other words, comprising all possible sets or possibilities. Now we come to the set of real numbers. Now the set of real numbers, as a matter of fact, is very, very, very old, known from the ancient times. In other words, you can say at least known for 5,000 years ago. But the study of it only began at 600 BC, where the Pythagoreans started to know that, for example, a number like square root of 2 cannot be put in the form of the ratio of two numbers A and B, where A and B are integers, for example. So, but even worse, they reckon that there are numbers which not only cannot be put in this form, but they're not algebraic at all, like for example pi or e. In other words, they don't satisfy an algebraic equation where the coefficients are rational. And so they started to look into this, these properties of R, and they came to discover that R is composed of many sets. The first one is the set of natural numbers, the one that we said before. We saw it before, that it comprised the numbers 1, 2, 3, etc., of which we count on our hand. And this set is meant to be closed. What do you mean of closed? Closed means that if you add up two elements in the set, you get another element in the same set, and when you multiply also two elements, you get another element in the set. So it's called closed under addition and multiplication. And then you have the set of integers. The set of integers, these comprise the set n along with 0 and the negative numbers. The 0 here is being known, as a matter of fact, since the very ancient times. The Greek knew them and some Mexican tribes, but the use of them came to be practical when in the Middle Age, when the Arabs substituted the Roman numerals with, like for example, they want to denote 10, so they put 0 aside with 1 to get 10, 2 zeros to get 100. Or you can, for example, they use them later on with decimals. Like for example, you have 0.12 means it's equal to 1 times 10 to the minus 1 plus 2 10 to the minus 2, etc. So the 0, it came to use at the very end. So whereas all the numbers have been discovered, the 0 have been discovered at the very end. Not being discovered, but discovered its use at the very end in algebra. For example, when you solve the equation, and this is why mathematicians called it the most civilized number, because its use at the very end. Now, for the negative numbers, they have been known a long time ago, but the meaning of them was not very clear, and this is why in the Middle Age they used to denote them by a red color. For example, if they wish to write -3, they put 3 and in red, and this is why from this come the word you are in the red when the bank tell you are in the red, meaning that you've drawn more than you did more transactions that the money you store in the bank. So these numbers here, the three of them constitute the set of integers, and they are closed under addition, multiplication, and subtraction. But then you have the set of rationals, and the set of rationals, this we encounter all the time. Is the set comprise all possible x satisfying bx minus a is equal to 0, where b is not equal to 0, and a and b element in the set of integers. So you can put them in this form: x is equal to a over b, where b is not 0, and a and b are integer numbers. Now, mathematicians thought that most of the number we deal with, because in the market and you always deal with rational numbers like half, third, 3 divided by 11, etc., that most of the numbers belong to this set, except very few instances like pi, e, square root of 2. You encounter very seldomly these numbers. So they thought that most of the numbers are rational, except very few instances where they are you have these numbers, until they discovered that the opposite is true. So they started to work on these numbers which are numerous. So they come up with a concept called cardinality. For example, the set n, a set like comprising 3 elements only, 1, 2, 3, is equal to the same cardinality like another set 3, 4, 5. And with the set, but when you have an infinite set like n, they give them a cardinality called aleph naught. And aleph naught is the cardinality of the set n, and any unbounded also subset of n also have the same cardinality. But what about Q, for example? When the set Q, here you have, for example, Q like 1 over 1 and 1 over 2 and 1 over 3, 1 over 4, 1 over 5, etc. These called have a one-to-one correspondence with the set n, of course. So they have the same cardinality. And of course, any other number in Q, you can put them, you can organize them in this way. Like, for example, you have 2 over 1, 2 over 2, 2 over 3, 2 over 4, etc. So they are called they have the same cardinality, and they are called countable sets because they are isomorphic to the set n. And any union of these sets also is countable, so they have the same cardinality as n. Now we see that the set R is composed of the set of rationals, and we have, aside from this, other sets which are called irrational, and irrational, they are numerous or more numerous than the set n. So now mathematicians, they wanted to classify these sets into first algebraic, for example, and non-algebraic. The algebraic are the rationals, along with square root of 2, square root of 3, they are still algebraic. And then aside from this, all the remaining. But they realize that there are numbers, they don't know where to put them, here or there. So they give this method of classification up to the more practical, because you don't, for example, say I'm going to buy an airplane for a square root of 2 million euro. So you have the rationals, which is more practical to use. Even pi itself, which is not an algebraic number, you use them in the rational form, 1.4, for example. So they have the rational, and then you have the irrational numbers. And then now we know that the set n is comprised in the set of integers, and z is comprised in q, and q is comprised in R, and even R itself is comprised in larger non-order set like the set of complex numbers, and here you have the whole set R. So now we have some algebraic and order properties. The meaning of algebraic properties, they have, you can manipulate with them with addition and subtraction. And like this, you have, for example, the set R, all the numbers, they adhere to the rule A plus B, 1 plus 3 is equal to 3 plus 1. So A plus B is equal to B plus A. We are not dwelling on this very much because these are known. The existence of the zero, this is the number when you add up to any number, you get the same number. The existence of the negative, and again, when you multiply by 1, you get the same number. When you divide, the reciprocal is the number which if you multiply by the original number, you get 1, etc. So the set R, in fact, has two set of properties, the algebraic properties and the order properties. In fact, mathematicians call it complete order field. What's the meaning of that? Field meaning it's closed under the algebraic operations. And it is at the same time ordered because any number on the straight line is seated in a certain place, and you know its relation with the number which preceded and the one after it. So it's called, it has an order property. And at the same time, it's complete. Meaning completeness, meaning that any non-empty subset of R, like a segment, for example, which has an upper bound, it has a least upper bound. And this is called complete. So the set R has these properties. It has algebraic properties, and it also had an order properties. Like, for example, A is bigger than B, and B bigger than C. So, of course, A is bigger than C, etc. And so now you have the set R. Now, along with this R, we can take segments, cut segments of R called intervals, because our functions are defined over, for example, value of x ranging between x1 and 3, for example, we're in between two values. So we call these intervals. So an interval is a segment of cut from R, and they can be, for example, here, the many alternatives you have on these intervals. For example, the first one here is called bounded and open, because the endpoints are not element in this interval. You have here it's bound and closed because A and B are two sets in the same interval, so the endpoints are element in the interval. It can be also bounded and half open, closed from one end and open from the other, etc. And you can also have this set. This is called open. Because it's unbounded, because like, for example, you say x greater than 3. So it's open from the part A, from the endpoint A, and it's unbounded because it goes to infinity. This one is closed. It's closed because the endpoint is the element of the interval, but it's unbounded. And then you have the set R, which is both closed and open, y we'll see in a while. So now we have also inequalities. Now relations in mathematics, they can be equations, like you say, for example, x squared minus 1 is equal to 0, and the solution of which give you a number. And then you have also an identity, like you say, sine square of x plus cosine square of x is equal to 1. This is called identity. Why? Because it's valid for all values of x. And then you have also what's called inequality. And inequality, you work up with symbols of this notation of this form. X is not equal to a. This one, x is less than equal to a, and you use it when you don't know the value of x, where it lies. But if you know exactly where x lies on this real line with respect to a, so you know that whether it is less or it is greater. These form of inequalities, they resemble equation because they are valid for all values of x, but we didn't mean, or valid for all values of a and b, but we don't mean those kind of inequalities. We mean the sort of inequalities that we encounter, and the solution of x, the solution of which gives you a set. So the solution of equation give you a number, whereas the solution of inequalities, they give you a set. For example, if you want to solve an inequality of this sort, x squared minus 3x minus 4 greater or equal to 0, what you do is that you decompose it into the product of two brackets. And here you have, because it's greater than 0, so either the first and the second both are equal to 0, or both are negative, less than 0. If both are equal to 0, then of course you get the biggest, because for example you possess more than 1,000 euro and more than 4,000 euro, so of course you possess more than 4,000 euro. So here, since it's greater than 4 and greater than minus 1, so it's greater or equal to 4. And if it is or, both are negative. It's less than 4 and less than minus 1, so it is less than minus 1. So now we have a union of two sets. Since it's either greater than 4 or less than minus 1, so x belongs to the union of the both interval. Here, it's a closed, unbounded interval from minus infinity to minus 1, or it is x is greater or equal to 4. Now, when you have intervals of this inequalities of this sort, this is a little bit difficult kind of inequality. What you do is that you try to the denominator you have to get to put it in a form where you have a form which is like this. You equate it here, 3, for example. Instead of it's on the right-hand side, you get it on the left-hand side, and then you have one denominator here, for example, and you wish to calculate the value of x. Of course, this is a set again. You value of x which satisfies this inequality. So what you do is that there are many ways to solve this problem. The best thing is that, for example, you have here a straight line to denote the regions of which x plus 1 is greater or less than 0. For example, x plus 1 is greater than 0 when x is greater than minus 1. So from minus 1 onward, x plus 1 is greater than 0, whereas less than minus 1, it's negative. And the same thing you have for x minus 2. X minus 2 is positive for x greater than 2, and it is negative when x is less than 2. And then what you do when unify, here you have unified the denominator into one denominator, you divide x plus 1 over x minus 2, and actually the same thing applies to multiplication, except because you divide them, then you have to exclude the number 2, because you can't divide by 0. So here you divide a region which is positive by positive, you get positive, and it is negative because here you get positive by negative, you get negative, and here negative divided by negative, you get positive. So actually, where are the regions in which x plus 1 over x minus 2 is greater or equal to 0? It's the two regions. Either x is greater than 2, you can't say 2 because you can't divide by 2, either x is greater than 2 or x is less than minus 1. So in fact, this is the solution, and it's a set, the solution of which any x belonging to this set would satisfy this inequality. It's the union of the two, one closed from minus infinity to minus 1, and one open from 2 till infinity. And this is the way how you write inequalities. You solve inequalities. Again, this is called an absolute number of A, and this yields a function, as a matter of fact. When you have an absolute value of x, it means that when x is positive, then the modulus A is equal to A, or when modulus A is positive, modulus is equal to A. And when A is negative, the modulus A becomes equal to minus A. For example, you have modulus minus 3 is equal to minus 3, which is positive 3. So for two numbers, A and B element in R, these all inequalities or expressions hold. The absolute value of AB is equal to absolute value of A times the absolute value of B. We shall not dwell on this because these are known. These are pre-calculus kind of expressions or relations. When modulus of A is less than B, it means that A lies between B and minus B. And same thing here, when modulus x, for example, is greater than 3, then x is either greater than 3 or less than minus 3. Now, this is a famous mistake which the students sometimes do. When they write square root of 9 is equal to plus or minus 3. The square root of 9 means the value of the square root at x equal to 9. This is a function, as a matter of fact. It's on your calculator. You are performing a set of functions. So the square root of x means that you are pushing the button of square root when you feed in, for example, the number 9. You get one number, which is 3. So the square root of 9 is equal to 3. And same thing when you have square root of x squared. It's not equal to x, neither it's equal to plus or minus x. Why? Because when x is positive, it's equal to x, but when x is negative, it's equal to minus x. And therefore, when x is negative, is equal to minus x, which is negative, so it's positive. So actually, the square root of x squared should be equal to modulus x. And this is one thing that we should draw your attention with. Again, the neighborhood. Now, what's the meaning exact of neighborhood? Now, the meaning of a neighborhood is something that mathematicians try to introduce in order to sort out problems of values that are nearby. And to give you an example, suppose, for example, you are in the United States and a friend of yours said, I'm going to visit Naples, for example. Show it to me on the map. So you get the map of Italy, and they tell you, for example, where is Naples. So he said, this is very near Rome. So you can say on the map, Naples in the neighborhood of Rome. But once you are in Rome, you take the plane and you arrive to Rome, Naples is outside Rome. Whereas the Vatican, for example, is in the neighborhood of Old Rome. And when you live in a building of the one that we live in, for example, the Vatican is outside, for example, is not in the neighborhood of your building, but your neighbor or the supermarket is in the neighborhood. So the neighborhood is something that mathematicians used to denote the region surrounding a point A. You have a point A, and you want to denote all possible values of a variable which lies in this neighborhood. In other words, lies in a distance from A, which is less than a quantity called epsilon. This is a fictitious or an arbitrary value epsilon that we denote the radius of this, or the location or the distance of your neighbor to you, to the point A. So in fact, it is represented in this form here. You have the point A, and I wish to call the set in which all the elements x are near A in a certain neighborhood, which I call n epsilon of A. So n epsilon of A is an open set comprising the point A, which at the center, and all possible x which are far by a predetermined distance epsilon. So either you put it in this form, or you can say it's an open set running from A minus epsilon to A plus epsilon. Now, this is an important concept. It's called the limit point of a set, which we shall be using all the time. Now, the limit point of a set is the point around which, if we construct a deleted neighborhood, the meaning of a deleted neighborhood, in other words, it's a neighborhood, the one we just explained, but we delete, we cancel it, we exclude the center. So this is called a deleted neighborhood. So either you say, the limit point of a set is that if you take any neighborhood to the point A, you can locate other points of the set different from A, or you better say, if you take any deleted neighborhood of the point A, you encounter points of the set. So if this is it contains at least one point of the set. So if this is the case, then here are two sets. This is an open set, and this is a closed set. Why? Because here the point 1 is an element in the set, whereas here the point 1 is not an element in the set. Whereas both, they have a property. The point 1 here is a limit point. Why is a limit point? Because if we construct any deleted neighborhood of the point 1, we encounter, of course, element in the set. And same thing here. If you draw any deleted neighborhood around the point 1, you encounter point of the set. So in both sets, 1 is a limit point, whereas here the limit point is an element in the set, and here the limit point here, 1 is not an element in the set. So we call this is closed. In other words, you can say that the closed set is the set that contains all its limit points. If the set contains all its limit points, then we call this set closed. Whereas if the set does not contain all its limit points, we call it open set, for example. For example, the open interval from 0 to 1, 1 is a limit point to the set, and yet is not an element in the set. But any point, for example, half, it's a limit point and an element in the set. So it contains limit points and points that are not element in the set and still are limit points. So since it doesn't contain all its limit points, but all its points are interior points, what the meaning of interior points? An open interval, any point that you choose, for example, equal to 1 minus epsilon, this is an interior point. Why? Because if you take any deleted neighborhood, like for example of radius epsilon over 2, so the point, the extreme point of this neighborhood is 1 minus epsilon over 2, and it's less than 1, so it's element in the set. So I call open set open if all its elements in the set are interior points, in the sense that if you took any neighborhood to this element in the set, you find it completely lying in the set. So here you have a neighborhood 1 minus epsilon, and you take the point 1 minus epsilon, which is less than 1, it's an element in the set. But if you take the radius epsilon over 2, you get the extreme point from the left hand side, 1 minus 3 epsilon over 2, which is element in the set. But again, 1 minus epsilon over 2, this value here is also an element in the set, and therefore this element, this number is an interior point, and therefore if the set is composed of all interior points only, you call this set an open set. Now we come to the Cartesian product. Well, the Cartesian product is a notation that we use to denote functions. In other words, we shall use this all the time to denote functions. Cartesian product, as a matter of fact, is a way of explaining the relation between two sets. For example, you have here a set A and a set B. And if you take all order pairs between A and B, you call this a Cartesian product. So here you have a two non-empty subset, A and B, and you denote the set of order pairs A and B such that A element in A and B element in B, you call this Cartesian product. The best thing to explain this is that, suppose, for example, here, this is an example which clarifies everything. You have A, the set composed of the three elements 1, 2, 4, and B minus 1 and 3. So the Cartesian product here is what? You take every order pair, you take every element from here associated with one element in the other set. So here you have 1 with minus 1 here, and 1 with 3, and then 2 with minus 1, and 2 with 3, and finally 4 with minus 1, and 4 with 3. So here you have the elements of A, as if you have a tree, and these are the primer, or the first branches, and then you have a set of secondary branches associating with A1, for example, B1 till Bm. And same thing with A2, B1 till Bm. And the number of secondary branches here are the number of elements in your Cartesian product. So this is the meaning of Cartesian products. Now, most of the time, when you associate two elements in the set, you don't take all the elements, but you take some elements which have some properties. Like, for example, suppose, for example, you have two sets, A and B, and you have a relation connecting these sets, these two sets, but you impose a certain property in this relation. So what you say is that although you have a Cartesian product, you take a subset of this Cartesian product and you call it XR of Y, meaning that this XR of Y is a subset of A, Cartesian product of A and B, but it adheres to certain property. Like, for example, suppose here you have an element, a set A and a set B, and you know how to obtain the Cartesian product now, but you necessitate that you choose a certain subset of the Cartesian product Q such that X minus Y is even. So now you don't take all the, you don't associate all X with all Y's, because you take only those, you choose only those that have the quality that X minus Y is even. So what you do, you start first by writing the Cartesian product. Now you have here 2 and here 3, so you must have 6 elements pertaining to the Cartesian product. But now you choose only those which you call Q, it's a subset of the Cartesian product, that have this property that X minus Y is even. So which you choose? 1 minus 1 is equal to 0, so this is even. And Y minus 3 also, it's even. 1 minus 4, it's not even, it's minus 3, so it's not even, so you don't take it. 2 minus 1 also, 2 minus 3 also, but 2 minus 4 is minus 2, which is even. So here you are only left with 3 elements in the set, and this you denote them by the set Q, having 3 elements, and it's subset of the Cartesian product, and those which only satisfy the relation that X minus Y is even. So the set Q now is a subset of the Cartesian product. It satisfies a certain relation. It's represented in the form, again, of the same form of arrows, but emanating from all the elements of A to the elements of B, such that X is element in A and Y is element of B, but not all the Cartesian products from A and B that you choose, but you only choose from those that satisfy a certain relation, which you call it Q. So, for example, here, this is a diagram showing the last example. Here, A is 1 and composed of 2 elements, and B, you choose, you associate 1 with 1, because difference is even, 1 with 3, and 2 with 1, you exclude it, and 2 with 3, but you associate 2 with 4. So now you have 1 associated with 1 and 3, and 2 with 4. So now you have the Cartesian product here. You choose from a subset Q composed of 3 elements, which is the ordered pair 1 and 1, and 1 and 3, and 2 and 4. For example, you have here an example. You want to draw a relation Q such that X minus Y on the axis X and Y, these are the orthogonal axes X and Y, such that Q satisfies the relation X equal to Y square. X equal to Y square, this is again a parabola but open from the right hand side. Here it is. So what you choose, you can of course, you can choose the set A and B to be the set of natural numbers, or you can choose the set of integers, for example. If you choose the set of integers, it just means that, for example, here the element, here the set Z, A, and here the set B. So you want to associate every element in A with every other element of B. For example, you can associate 1 with 1, or 1 with minus 1. For example, since X is equal to Y square, it just means that if X is equal to 1, Y square is equal to 1, which means that Y is equal to either 1 or is equal to minus 1. Here is like this. Here you, with X is equal to 1, Y could be 1 or could be minus 1. And same thing, you go along like this with all the elements of Z in the first set. But then you are stuck with a problem. You're stuck with minus 1. Now, if X is equal to minus 1, Y square is equal to minus 1. So there is no such real Y satisfying Y square is equal to minus 1. So this element minus 1, there is no such element in Y corresponding to this minus 1. So now you have a problem. Sum of elements of X corresponds to 2 elements of Y, but there are also elements in X which do not correspond to an elements of Y. So in this example, we saw that we took an example which is very clarifying. First of all, you have two sets, A and B, and you have a Cartesian product between the two sets. A Cartesian product is a set of order pairs. You associate every element in A with another element of B, but you can always impose certain relation on this association, because you may not want to take all the possible order pairs between A and B, but you may want only to choose some pertaining to a certain relation. So you call this Q, and this Q gives you a subset of the set of the Cartesian product which satisfies this relation. Like, for example, the example that we saw before. Here you have X is equal to Y squared. So, for example, you want to choose those from A pertaining to this relation. So, -1, for example, you cannot be associated with elements in Y, because Y squared is equal to -1 does not exist, a certain Y real satisfying this relation. And in this particular example, we also saw that one element in A, in the first set, is associated with two elements in Y. So in this example, it's a very clarifying example. X is equals 1 in A gives two values in B in the second set. And again, X is equal to -1 in A has no image in the set B, because there is no such Y satisfying Y squared is equal to -1. So in this example here, we have these two problems, that one element in A gives 2 in B, and there are elements in A that do not correspond. We don't find corresponding values on B. But if we find for each X in A there exists a Y in B, i.e. there is an arrow emanating from every X in A, this is the first assumption that we have to adhere with. And if this arrow is unique and ends up in a unique point B, because we saw in this example that it ends in 2 points, then in this case we call Q a function. And a function Q, it's a relation of order pairs relating elements of A with elements of B pertaining to a certain rule, but such that we have to make sure that every element in A emanates from every point in A. In other words, there are no elements that have no correspondence in the other set B. And at the same time, every element in A emanates in the image set B, emanates only one arrow, not two arrows. In other words, corresponds with one element, a unique value in B. Then we call Q a function. And we call the A, from which the arrows emanate, the domain of this function. And the elements of B, of which the arrows ends, we call it the domain of the function. And this is actually the topic that we shall discuss in detail in our next lesson. So in this lesson now, we exposed all real numbers, and we saw that real numbers is the union of many sets. And we discussed we saw how that the set Q is countable, and this is the set usually that we define our functions upon. But there are also the real number R, set R, that contains all the real number that we shall deal with, because our functions are dealt with on this set. And we saw the properties of R as well, and we saw how we can associate numbers together from two sets, which we call the Cartesian product. And when this property, when we have a certain property that we choose that satisfy certain conditions, that you associate order pairs, that you have a one-to-one correspondence from each order pair, from each number in the first set to the number in the second set, we call this a function. And this is, as I said, this is a subject that we shall discuss in great detail in our next lesson. So until we meet, I like to draw the attention that all these lessons, the one that we started with today, and again with the other lessons that we shall be teaching, all are uploaded to the site of the Uni-Nettuno Telematic Universe. So until we meet, thank you for your attention, and thank you very much.